This is artificial intelligence. Um, I'm going to start really quite slowly with this, and there are good reasons for that. And those reasons are really to do with the fact that artificial intelligence always has and continues to get people very excited, but they don't necessarily know what it is or why it is the way it is. And exploring those things a little at least serves the purpose of planting the goalposts so that we know where they are. So I'm going to initially talk quite a bit about what it is that we're trying to do, the history of this whole pursuit, how people approach it, and I'm going to try and talk a little bit about agents, which really just gives us a context and a structure that we might hang everything else on. I will make various references to AIMA. This is Artificial Intelligence, a Modern Approach, okay, which is the main text for the course, and I'll say something more about that a little bit later. So, off we go. AI, you will no doubt have noticed, is currently extremely heavily hyped. This is not a new thing. It's at least the fourth, possibly the fifth time in history that it's happened. These hype cycles seem to be periodic. I became interested initially as an undergraduate in electronic systems engineering in AI because it became a subject of great hype during the 1980s. The reason it became a subject of great hype back then was that people got very interested in these amazing new things called neural networks. And in fact, an awful lot of what you hear about neural networks now is not really much different at all to what was being done in the 80s and even decades before that. So you're hearing a lot. You're hearing an awful lot about how wonderful and transformative AI is and is going to be. But I would claim that a lot of it is very, very overblown, just as it has been when there's been a hype cycle in the past. So you will hear an awful lot from people with something to sell, and an awful lot from people with a philosophical bent, because this seems to be where a lot of the hype comes from. Why is that? Well, people with something to sell, I mean, it should be obvious why they might want to hype this stuff up. Why philosophers? Well, if you're a philosopher or a psychologist, then you might have big aims, namely to understand humans and what makes us intelligent, how this can be, what it means. And philosophers have been thinking about this for a long time. More recently, you will also have heard them talking a lot about the ethical implications of AI. But that goes back a while as well. They've often asked, can we or should we do AI, and what might the consequences be if we achieve it, in the sense that we actually end up being able to produce something that acts intelligently on the same level as a human might. Philosophers have also tried on many occasions to argue that AI is impossible. That hasn't worked out too well for them. Usually, and I caution you here, if you claim that AI can never achieve something, it quite often doesn't take too long for it to be achieved. There were a bunch of philosophers around many years ago who probably felt very silly having claimed that an AI would never beat the human world chess champion when they saw Kasparov get beaten. So, philosophers have talked an awful lot about AI, and they continue to, but it's fairly noticeable that philosophy hasn't really given us much, if anything at all, in the way of results. And there's a good reason for that. philosophy is good at asking questions. It's not necessarily so good at answering them. So how might we think about it differently? Well, it's a really interesting question from a perspective of being the study of a certain kind of computation. Brains are small. That much is definitely true. They may be slow. That's not quite so clear-cut. The actual things that neurons do are pretty damn complicated and actually quite hard to simulate. So we can leave that one open. But unless you want to take a really hard-line position of saying that brains aren't really doing computation, and there are philosophers that will take this position, we have to accept that there is some form of computation going on there. And it would be nice to be able to make systems that can do the same thing. But then we get to the third point, which is we want to make and sell cool stuff. Because we're technologists, computer scientists, and that's a key part of what we might be wanting to do here. But the wider aims of just understanding what's going on are perfectly reasonable. On the subject of brains being small and slow, maybe, they're also incredibly power efficient. They take far less power in order to operate than the processor chip in your laptop. And that in itself is really quite remarkable. They're also way, way more complex than you think, unless you've spent a long time studying neurophysiology and neuroscience. They are far more densely put together than the best of anything that Intel can produce, even with their densest current process. And they're in 3 dimensions. And making microprocessors properly in 3 dimensions is actually pretty tricky, because you have to get rid of the heat somehow so the thing doesn't catch fire. Okay, so brains really are a remarkable thing, and they're worthy of study in their own right. But we want to make and sell cool stuff, and we want to understand computation. And it's notable that quite often when you hear philosophers talking about brains and AI, that it's clear that they don't seem to have had your advantage, which is to have taken a course on theory of computation. The Church-Turing hypothesis is a powerful thing. Do you think your brain is a Turing machine? I'll leave that one for you to think about. And the great thing here is that when you take this from a perspective of wanting to make and sell cool stuff, that seems to be a much more successful way of approaching artificial intelligence than philosophy on its own. Now, another point here, and the final one for this slide, really is that you hear a lot at the moment about how AI is revolutionary and suddenly it's living up to its promise. This is all a massive misperception. AI has been in your life for decades. It's been sitting there doing interesting things without you being aware of it. I went to talks in the 1990s on how it was being applied by merchant banks to do currency trading. There were people in the 90s doing perfectly interesting AI research applied to drug design. And to any other number of applications areas that you can think of. This stuff was being deployed and sold and working entirely successfully decades ago. Okay, this is not a new thing, so don't be led astray into thinking that it is. Nonetheless, we're still in a really good time to be doing research on AI. It's a very young field. It's only existed arguably since 1956. I would say it goes back a bit further than that. You can find work on very basic neural networks that goes back way before 1956. And And you could probably argue that even back as far as the 19th century, the mathematicians were doing work that's relevant. But that would be sidetracking. Because it's such a young field, it's a bit like being around in the very early days of physics, before physicists knew anything about atoms or gravity or any of this stuff. It's possible to do interesting things, genuinely interesting things, because we're still very early on in the process. Now, there's a bunch of small print here. Maybe I've been a little bit hard on the philosophers, poor things. I'm not going to look at this small print here in detail. It just gives you a very quick historical summary of things that philosophers have thought about that you can probably see reflected in the modern approach to AI. If you want to read more about that, AIMA, Artificial Intelligence and Modern Approach, has quite a lot of material on the historical and philosophical background, and if you're interested in that, then by all means please do read it. But the real essence here is that for this course I want to take a much more applied approach that's based on making stuff that actually does things. Okay, having said that this has been perfectly successful for a long time, what sort of things have actually been achieved here? Well, this is just a fairly short list. Perception isn't necessarily regarded at the moment as a fundamental thing within artificial intelligence. Well, depending on what kind of perception it is, certainly vision and speech processing have been around in AI for a long time. Inference of emotion from video has been around for probably a decade. Seeing, enabling, touch sensing, artificial noses have been around for a while. You can be sniffed when going through security at the airport because artificial noses can detect explosives and drugs and all sorts of other things. Logical reasoning, again, it's been around for a long time. Prolog, which you now have had an introduction to, was one of the fundamental things in AI for a long time. In fact, there was an awful lot of money spent in the 1980s trying to make a good, high-quality human-level Go player by building huge lumps of hardware that would run Prolog. This was not successful, but Prolog itself is a little microcosm for logical reasoning, and I'm going to come back to that a bit later in the course. Expert systems have been used successfully for medical diagnosis over many, many years now. Psych is a knowledge representation reasoning system. The company that produces Psych has been going for years and years and years. I could go through the rest of this slide one thing at a time, okay? But the take-home message here is that, again, AI, in terms of being a successful, applied and saleable entity, is not a new thing. It already has many, many successes. What I will note at the very end of this slide is that an awful lot of those successes do not involve the word deep. Okay? Things with the word deep in them are where the real hype lies right now. And there's very, very interesting work being done. We cannot deny this. But people at the moment have a definite tendency to conflate deep learning with AI and to claim that they are the same thing. They are not. One of the things that I want to bring out in this course is the fact that AI is a much, much wider field than just deep learning. And there are notable algorithms and methods and successful applications that have nothing at all to do with deep learning. Okay? Deep learning is part of AI. It is not AI. If I'm going to talk about what's been achieved, I should also take note of the fact that there's still a very, very long way to go. You will no doubt form your own opinion on when you think AI might get to the point of being able to tackle human tasks at the level that humans can tackle them. Okay, it can already do some things pretty darn well, but there are plenty of things that it can't. Now, I heard this example in a talk by a philosopher, believe it or not, Margaret Bowden. This is a line from Shakespeare's Macbeth: "Sleep knits up the ragged sleeve of care." This is an example of something that no AI on Earth at the moment can really form a good understanding of. If you doubt this, try going on to your favourite translation service, translating this from English into a non-Caucasian language like Arabic, and then translating it back again and see what you get. You will invariably find that all nuance of meaning is lost in that process. This is a very, very complicated sentence to try and get an AI to understand. Sleep knits up the ragged sleeve of care. We know what this means. It means that if you feel rubbish, having a good sleep might make you feel better. But there's all sorts of nuance going on here. It's conflating the idea of a person just feeling not very good with a ragged sleeve, a sleeve that is in some sense broken. That's being used to stand in for care, the ragged sleeve of care. Knitting up a ragged sleeve would repair it. In some sense, it's making the care go away. And, well, sleep doesn't knit, people knit, machines knit, but we can say that sleep, in a sense, cures something, and the knitting here is the cure. So there's a lot going on in this sentence, and AI really isn't at a point where it can actually handle interpreting that kind of language in any effective way. I suspect that's going to take a while. Okay, but I think we're a long way away from that right now. There's also another thing to bear in mind, which is that when AI has a success, people tend to stop thinking that it's AI. We've observed this for years and years and years now. Well, I would be interested to know whether you consider the fact that your phone can do speech recognition as being a form of AI or not. Speech recognition, effective speech recognition now, is a decades-long research program. It's taken decades to get to where it is, and for a long time it was very, very firmly planted as an activity within artificial intelligence research. Now it's just something that your phone does. Okay? Do you consider it AI, or would you consider it AI if I hadn't pointed this out? I don't know. You'll make your own mind up about that. I have no doubt. Now, at this point, I want to actually get into some historical context. The question of what is AI may seem a little bit nebulous, but from a historical perspective, it's quite important, because the way in which people have thought about it and the way in which they have approached it depends in a very definite and quite important way on the background that they're coming from. Now, there's a very rough categorization here, and it gives us 4 different perspectives, okay? 2 axes. Do we want to know about how a system acts, or do we want to know about how it thinks? The other axis is, do we want AIs that work like humans, or do we want AIs that are rational? And here rational has a particular meaning. It just means doing the right thing in the right circumstances. Okay? This is not something that humans always do. Okay? We might want rational agents, not human ones. Okay? But the way in which people, excuse my email, the way in which people have approached AI depends heavily on where the background that they're coming from, and it tends to put them at one of the 4 points on these 2 axes. So let's now just have a look at what each of those 4 points comes out like. The first possibility here was proposed really entirely by Alan Turing in what something you've probably heard of, the Turing Test. This is an approach to artificial intelligence that casts it in terms of making something that acts like a human. Okay? If you haven't heard of the Turing Test, it's very simple to state and incredibly hard to pass. You allow a human judge to interact with an AI program, and all they have access to is a computer terminal. The point of the game is to see if the judge can decide whether or not the thing they're interacting with is a human or an AI. And you can make this more interesting. You can have the unrestricted version of the test, where the AI program may have a camera attached, it may be able to listen, it may have an arm that can be used to manipulate things. Okay, you can make it as easy or as complicated as you like. But the important point is that the claim here was that an AI is a proper AI if a human can't tell the difference between the AI and another human. Now, you may have heard relatively recently news reports that this test has been passed. I will very happily claim that it has not. If you want to take a look at how far away we are from passing this test, try taking a look at something called the Loebner Prize, where this experiment is allowed to run, typically with chatbots. It is really very easy to tell the difference between the best chatbots and a human. And if you look up some historical episodes of the Loebner Prize, you can see some transcripts. You will probably also find links to online versions of the chatbots so that you can try this yourself. Now, in many ways, this is quite a nice way of thinking about AI, but it's not perfect. Clearly, in order to pass this test, you would have to produce an AI that, in a sense, has many of the capabilities of a human, particularly in terms of stringing sentences together and being able to deal with a very wide range of background knowledge. But it's arguable whether a human child could pass this test or not. And I would argue that even quite young children are clearly intelligent, okay, in a very human way. There's another point that makes this way of thinking about AI less than perfect for our purposes. And it's that while AI as a wide subject has always concentrated on getting things that are in some sense human-like, we might actually not need that. AI in its modern sense goes an awfully long way beyond attempting to produce things that are simply within the domain of humans. If, for example, I had an utterly brilliant expert system that could ask a few questions and tell you whether or not someone is suffering from a particular condition, you might regard this as useful whether or not it can produce any kind of an explanation behind its reasoning. And it's that explanation that is a very human-like trait. We also want really to be able to design AIs that are effective in environments that humans cannot exist in. It is a problem of considerable importance, for example, to produce autonomous underwater submersibles that can work in the dark at extreme depths and can do so effectively. And this is clearly something that humans can't do. Okay, so the Turing test is a historic and famous thought experiment, and it deserves its place in history. But it does have its problems. The second possibility is to think of AI in terms of making things that think like humans, okay? Not act, but think like humans. And this is something that comes out really of the psychological perspective on AI. Unsurprisingly, psychologists have asked very similar questions to computer science in this respect, because understanding how humans think and work within the world is very much a psychological aim. The field of psychology and experimental psychology, however, took a bit of a different perspective to the one that Alan Turing did. Not surprising, because psychologists are trained in psychology and Alan Turing was a mathematician. The way in which psychologists tried to do things was to get people to actually do tasks while introspecting on how they were doing the task. And they would then get people to write down the results of that introspection and try and write a program that did the same thing. In a nutshell, that's what gives you cognitive science. Psychology, trying to get out of people how they're doing things, and computer science, writing programs to try and do something similar. The really big, famous example, early example of this is the general problem solver of Newell and Simon, because they were trying to make a system that in some sense reasoned in the same way as a human. There's a lot of work on this. It turns out that it's very difficult to do this kind of experiment without, in some sense, biasing the subjects in favour of the underlying theories that are being put forward by the lab in question. This led ultimately to something called behaviourism in psychology, where this kind of experiment was entirely rejected, but I'm not going to go into that in more detail. The third perspective, okay, sometimes thought of as the laws of thought. Now we're talking about trying to make AI systems that think rationally, okay, not think like a human, but think rationally. This essentially comes down to mathematical logic, and consequently is often referred to as the logicist approach to artificial intelligence. And this was a huge driving force in AI in the 70s in particular. In fact, pretty much the entire of AI during the 1970s was based on this logicist approach. And the idea here is straightforward. You have seen how to represent certain things in terms of first-order logic or some other kind of logic. It's not too big a step to consider the possibility of representing knowledge about the world in a logical calculus of some kind. And if you can do that, you can represent knowledge about how actions affect the world. And then you can think about using inference to come up with sequences of actions that affect the world in the way that your AI wants to affect it. This is perfectly possible, and I will be talking later in the course a little about how you can try and do that within first-order logic in particular. It did, however, come up against some extremely harsh, fundamental limitations. In particular, although you can represent knowledge about the world in a mathematical logical calculus, such as first-order logic, it's very, very difficult to deal with common sense knowledge or uncertainty. Those are two big sticking points. Logic comes out with hard-edged results. Is something true or false? Is it tautology? Is it satisfiable? There is little room, if any, there for dealing with the kind of uncertainty that any kind of AI acting in the world would have to be able to deal with, and which we deal with really without thinking at all. It's also very difficult to represent common sense knowledge. You can represent facts, and you can represent rules, and you can chain rules together, and you can do quite a lot, but the kind of common sense knowledge that we use for a lot of our lives in order to function within the world is almost impossible to represent. Now that ultimately led to a huge change in the last 2 or 3 decades in how people think about AI within computer science, and this is clearly a very computer science-centric way of thinking about AI. More recently, the need to deal with common sense and uncertainty has led to an approach to AI that's much more firmly based in probability. Okay, probability is really the gold standard now for dealing with uncertainty. And I'm going to come back to that again in a moment. But I won't really, in this course, get into how you do AI with probabilistic approaches. That's for machine learning and Bayesian inference next year. The other real sticking point for the logicist approach was computational complexity. Okay, you know that even in the simplest logic, propositional logic, SAT, deciding satisfiability, is NP complete. Okay, all right, well, actually, it's probably a bit early because you'll be doing the computational complexity course at the same time as this one, won't you? But it's the SAT problem, the problem of taking a Boolean formula and deciding whether or not it's satisfiable, is, as far as you need to be concerned at the moment, an exponential time problem. Inference in first order logic is even worse. Inference in first order logic is undecidable, okay, in the sense that you came across in the computation theory course last year, or last term in fact. And so you can really get bogged down in computational complexity in trying to do AI in this way. And the final 2 points here are, of course, that sometimes you need to act even when you can't infer what to do if you have a purely logical system. And sometimes you want to act fast without trying to think too hard. Okay? Sometimes you want a reflex action. All of these things are difficult in the logicist perspective. Now, the fourth possibility here is that of acting rationally. Again, not acting like a human in the way that Turing put forward, but acting rationally, doing the right thing given the circumstances. Now, this isn't so much really just a fourth point within those two axes. This is more a synthesis from which the other three perspectives naturally follow. And it doesn't come out really so much from a particular subfield's way of looking at the problems of AI. Okay? If you think in terms of making AIs in such a way that they achieve goals, given beliefs represented in some way, you almost inevitably get the usual subfields of AI, which for the purposes of this course contains things like search and planning and knowledge representation and reasoning. Very naturally, these things come out of this way of thinking pretty much on their own. In addition to that, we have the freedom to think about things like actions and goals and beliefs in a fairly precisely defined way, because we get to define them for ourselves. And that in itself is an improvement on any kind of approach where we try and model AI systems on humans. Because if we think about humans, we can't even propose any sensible definition of what something like a belief or a goal is, because we don't know how those arise within our heads. It also doesn't make so much sense to base things on humans, because humans are a system that's still changing and adapted to a specific environment. And again, as I pointed out earlier, we might be interested in making AIs that work within environments that are extremely inhospitable to humans. all the things that are needed to pass the Turing test would seem to be necessary to make a system that achieves goals given beliefs, acts rationally. So it seems to naturally take in the approach of acting like a human. And similarly, it seems to take in quite naturally the idea of the logicist approach, because that clearly forms part of what might be required to make AIs that achieve goals given their beliefs. In other words, act rationally. So really this is a synthesis that leads in quite a nice way to a conception of AI that's actually the most useful to us. Okay, so this is the one that we're going to take. AI systems, as far as we're concerned, are systems that act rationally. That means that they have beliefs and that they can use those beliefs to achieve some underlying goal or goals. Now I'll say something just fairly briefly here about other fields that have contributed to AI. This is expanding a little on some of the stuff that I've already said. I used to spend a lot more time on this, but I wanted to make more room in the course. So I'll mention some things here fairly quickly. You can read this slide in more detail at your leisure. And once again, in AIMA, there is a lot more about how these different fields have had an effect on artificial intelligence. The reason that I want to say something more about this particular part of the history is that I think many people don't quite appreciate the fact that so many different fields have an influence on the modern conception of artificial intelligence. Now let's go around anti-clockwise, starting from the top left. Experimental psychology I've mentioned, okay? But there are other things in experimental psychology, particularly the study of the visual system, that have had a sufficient effect on AI still to be relevant. The experiments involving introspection turned out to be dubious, and that led to behaviorism. That in itself had its own shortcomings. And so Craig, in his book The Nature of Explanation, then went a little bit further within experimental psychology and actually came up with something very close to the rational action approach that we're going to take. He had the idea of the brain as an information processing device that had beliefs and goals and could reason. And the system, importantly, has a model of how the world works that is represented internally. That's very close to the kind of model that we're going to be basing things on. It shouldn't come as a surprise that linguistics has had an influence on our AI. There is another course on natural language processing, which you may be taking. But Skinner famously had a book called Verbal Behavior on the behaviorist approach to language, which Chomsky later essentially overturned because he pointed out that it can't account for the fact that people can produce sentences they've never heard before. That part of AI, natural language processing, as I pointed out, sleep knits up the ragged sleeve of care, continues to be a really central and important sub-area. Cybernetics. Okay, probably not a surprise that this has had an input in AI, because robotics is clearly a related area. This goes back a long way. You can think of something as straightforward as a steam engine governor or a thermostat as being a form of AI system. A thermostat works within an environment and arguably has a goal, which is to keep the temperature in a particular place, and it acts on the environment in order to do that. Since then, we've had the whole subject of control theory in terms of how you act on a physical mechanism to make it do what you want it to do. And that's led to stochastic optimal control and all manner of other things that are extremely closely related to an awful lot of modern AI. Economics as a field is probably something that you wouldn't usually consider as having had an effect on artificial intelligence. But the thing with economics is that it tends to be looking at problems like, how do we act when there are adversaries around to obtain nice stuff in the future? This is a microcosm of AI. And in particular, in modern AI, the idea of decision theory, okay, which involves measuring the utility from your AI's perspective of a particular state of the world, and then using probability to work out a way of acting under uncertainty, such that over time, your expected utility is maximized. Okay, this is a fundamental approach within modern AI, and it has its roots entirely in economics. And then we also have game theory, which is about how small economies work, and has come up with insights like, for example, sometimes it's rational to act randomly. And we have Bellman's work on, in particular, things like Markov decision processes, which are a fundamental part of the underlying theory that supports reinforcement learning. That's a big thing right now. Neuroscience, clearly, this has had an influence on AI, and a lot of that comes through the fact that when people have bumps on the head, it can affect their behavior quite badly. And by studying which bits of brain have been damaged by bumps on the head, we might get some insight into what those pieces of brain do. And finally, mathematics. Okay, I've also already mentioned logic and probability, and these have fed into modern AI in a very current and significant way. So, having said a fair bit about the history of the subject and how it's got to look the way that it currently looks, here's what I'm going to talk about in this specific course. I'm going to start just by talking about the idea of an agent. We're going to get that out of the way pretty quickly. An agent is just the modern conception, if you like, of what an AI object is. But we will refer to agents because that's the modern parlance. Initially, I'm just going to talk about the simplest possible kinds of algorithm that you can use in artificial intelligence, and these are intelligent search algorithms. Constraint satisfaction problems are then one way of having very, very generic and general search algorithms that can be applied to a whole bunch of different problems. Intelligent search in its own right tends to require you to do a lot of handcrafting to adapt the search algorithm to the problem at hand. Constraint satisfaction is more general. Search, when you then modify it to work in the presence of an adversary, leads to game playing. So I'll talk about the classic approach to producing agents that can play games. And you can probably see that there's sort of a working up in complexity here. We go from search to general search to games, then to knowledge representation and reasoning. We've talked about wanting agents that can act rationally, in the sense that they can have beliefs, which we need to represent in some way, and which want to attain goals. And for that, we need to be able to reason on the basis of beliefs to work out what to do next. Now, in a sense, reasoning and search are very closely related, okay? But reasoning tends to be more complex because it's within a logical framework. Now, we can also cast this idea of using beliefs and then trying to work out what to do to achieve goals as making plans. That leads to a different perspective to the search or knowledge representation and reasoning approach, and leads to specific algorithms for constructing plans that can then be put into action by an agent. And the final thing is to talk a little bit about learning on top of all of this stuff, specifically using neural networks. And these are only one approach to learning. Again, learning is a sub-part of AI, and neural networks are a sub-subject within machine learning. But I'll give an introduction to this towards the end of the course. Now, this particular lump of content is quite often referred to as good old-fashioned AI. This is in some sense accurate, in that this is a summary of the central areas of AI that have been built up since 1956, or possibly a bit earlier than that, and now form the core of AI application areas. The old-fashioned part is possibly misleading. Each of these areas continues to be relevant and applicable in producing agents and AI systems in general. So although you will hear this stuff referred to as good old-fashioned AI, don't make the mistake of thinking that means it's not actually used, because it most certainly is. And as I've said before, I'm not really going to talk about uncertainty in this course. That's something that I'm going to talk a lot more about in machine learning and Bayesian inference next year. Let me say something briefly about what's not in the course. I'm not going to talk about Prolog or Lisp, even though they're classical AI languages. Really, the language you use to implement AI these days is probably, depending on how fast you want to make things and what particular area you're working in, going to be C++ or Python or something. Having said that, large chunks of IBM Watson were actually implemented in Prolog for very good reasons. But I'm not going to go into those any further. I'm not really going to talk specifically about vision or hearing or speech or touch or taste or smell. These are huge areas in their own right. As is natural language processing, you have a separate course on that. You guys are not electrical or mechanical engineers, so I won't be talking about robotics. Now, I do need to say a little bit more about the next point, which is I'm not going to say anything much about genetic algorithms or programming or swarm intelligence or artificial immune systems or fuzzy logic. The reason for this is, and now I'm going to be moderately controversial, let me sidetrack slightly. If you look at the biggest conference in AI at the moment, which is NeurIPS, you can probably go back a few years and find basically nothing in any of these subjects. The real hardcore of effective AI research has moved on from these concepts. You will still find research done in all of these areas. But the real problem here is that they are, in quite a real sense, subjects whose names have been deliberately chosen to make them appealing. Whereas really, they're not doing anything that unusual. So for example, genetic algorithms and genetic programming, these are ways of doing optimization. Fuzzy logic is essentially a way of having logic with values for uncertainty attached to it, and is therefore a competitor, if you like, to probability. In any case, for genetic algorithms and programming, there are other ways of doing optimization um, that are very often more effective. Genetic algorithms and programming do have a place because they can do optimization where the representation of the solutions you want to find isn't really convenient for other optimization methods. Fuzzy logic, on the other hand, a lot of experiments have been done comparing it with probability, and we generally find out that probability works better. That's why if you look in NeurIPS, you will find an awful lot of probability and no fuzzy logic. So I think that given I have a mere 12 lectures to give you an introduction to AI, these areas are less interesting and less important. And I suspect in the future will continue to be a bit more of a niche within modern AI. I'm going to give you some suggestions for reading. The first suggestion here is by Francis Crick, one of the two people who discovered the structure of DNA. And this came out in 1989, and almost every word in it is still entirely relevant today. Crick looked at the great excitement about neural networks in the 80s and wrote this paper in response. It is still entirely relevant. The Loebner Prize I've already mentioned to you. Marvin Minsky, another big name in computer science, wrote Why People Think Computers Can't. A critique of why the philosophical proposal that you can't make computers think may not stand up to scrutiny. The reference to go here is the paper published in Nature on the initial successful attempt to beat a human expert at playing Go. The Psych project, this is its homepage, and I've mentioned that already. And the final point here is I'm going to suggest that you look at the NASA Ames website, because NASA have done an awful lot of work over the last decades on AI that they put into satellites and robots and all manner of other clever things. I'm also going to suggest that you look at these publications, which are quite recent, high-level looks. Well, the first two certainly are quite recent, high-level overviews of AI within the UK and elsewhere that you can learn an awful lot from, because they've been quite carefully considered by people who really know what they're talking about. The final suggested publication here that you look at is Building Machines That Learn and Think Like People, which is a really very good and interesting revisit to the idea that perhaps you do want to learn something from the way in which people think and incorporate that into AI, and it gives some very good arguments for why we maybe shouldn't entirely dismiss that way of thinking about things. The main text for the course is AIMA, Artificial Intelligence, A Modern Approach. If you wish to look at an alternative, there's another recent book here, Artificial Intelligence, Foundations of Computational Agents. The remainder of these books are more detailed treatments of specific subjects within the course. Okay, so these correspond to the points on the earlier slide where I talk about what the course covers, and these are books that will cover things in much more detail. The prerequisites for the course are important. The prerequisites are, you're going to need to know about first order logic, the stuff that you covered last term. You're going to need to know some stuff about algorithms and data structures, and you'll need that right from the outset. I'm going to talk about continuous and discrete mathematics, and I will make regular mentions of the computational complexity of some of the procedures that we're involved in, because these are important. But the real thing I want to impress on you right now is this. You may have thought that when you finished NST Maths, you were never going to have to do that stuff again. I'm afraid that is not the case. You're going to need to know about calculus. And if you want to carry on to next year and do machine learning and Bayesian inference, you will need to know quite a lot of calculus and quite a lot of linear algebra and quite a lot of probability. If you want to understand machine learning in particular, and everyone wants, it seems, to understand machine learning at the moment, you really need to have that stuff under your belt. So, if you've forgotten how to differentiate, if you've forgotten how to handle vector submatrices, you need to go and remind yourself. If you don't, then when I start talking about backpropagation and neural networks, you will get lost. I absolutely guarantee it. Now, you can self-test yourself. Here are a couple of questions that you can try and do. If these are challenging to the extent that they mean nothing to you, or you can't get to the end of these questions, please, again, go back and look at your NST Maths notes. You will need this stuff later on in the course. Now, finally, I'm going to just say something quite important about computational complexity here. I will probably use the term AI complete. Now, once you get a bit further through the computational complexity theory course, you will know what this blah complete term means, okay? You probably won't have a good understanding of it now, but when I say that something is AI complete, essentially what I mean is that it's something that's only solvable if you can solve all of AI. Sleep knits up the ragged sleeve of care. Getting an AI that can really understand that kind of sentence is probably an AI complete process. Okay, so when I say AI complete, that's what I mean. Now, that has in the past been somewhat misconstrued. Okay, this is from some course assessment feedback. Someone complained that I say that basically everything in AI that's interesting is computationally hard. Okay, it's NP complete. Okay, and again, for now, just assume that that means it's exponential time complexity. Okay, you'll understand it better once you get further through the computational complexity course. When I say everything in AI that's interesting is NP complete, I mean it. Basically, AI is really hard from a computational perspective. Now, one way of interpreting that is to say, well, it's all a waste of time. If everything's exponential time complexity, then why are we bothering? Okay, it's very interesting that our brains can do this stuff, but why are we bothering if it's all that tricky? Well, that's an understandable interpretation. But you have to remember that if something is worst case exponential time, or if something is NP complete, it doesn't necessarily mean that you can't solve big instances. Now, I will use Boolean satisfiability here as an example. This is an NP complete problem. But in practice, it's possible to solve absolutely huge instances of Boolean satisfiability by using some clever programming. Okay, so the fact that something is NP complete or exponential time or whatever isn't a reason to completely discard it. You need to be aware of the fact that it's hard, but you shouldn't just throw it away entirely. What you can do is turn around and make it an opportunity. You can say, well, if we can't solve it perfectly, can we solve it well enough in practice within a reasonable amount of time that our result is useful? Okay? Can we find an algorithm that's good in practice in the sense that it will often find a good, not necessarily optimum, but a good enough solution using just a reasonable amount of time and memory? An awful lot of modern AI comes down to precisely this: designing really good approximation algorithms. Okay? Not trying to find the best possible solution, but trying to find a good enough one in a reasonable amount of computational resource. Okay, so that's important. Lots of things, practically everything in AI is hard, but that means not that we should throw it away, but that we should design good approximation algorithms.